Mathematical ideas have often been used to create structural forms in writing. We're going to explore some of these today, playing around with the various layers of meaning in the phrase, the structure of a story. And this will give us three main threads of discussion. The first of these is the structure that we can give a piece of writing by using some kind of formal constraint. When we think about constraints as used in writing, the key figures in this movement are the Oulipo. This is a group of writers and mathematicians. Oulipo is a contraction of Ouvroir de littérature potentielle. The group was formed in November 1960 and has had many well-known members, including Jorge Perec, Raymond Queneau, Italo Calvino, even Marcel Duchamp. So there's lots of good and exciting literature that's come out of this movement. The idea of the Oulipo is not per se to create the literature itself, but to give examples of or set up potential constraints or forms for literature. So this is potential literature. I want to start by showing you a humorous piece by Raymond Queneau called Foundations for Literature after David Hilbert. So David Hilbert, of course, a very famous mathematician, and one of the things he's famous for is for giving geometry a more formal axiomatization, kind of following from Euclid, but he made it more rigorous and he gave lots more axioms. And the important thing about David Hilbert's axioms for geometry is that by changing perhaps what we understand by the terms involved, point, line, plane, and so on, you can give examples of many more kinds of geometry than the standard Euclidean geometry. So I want to just give an example here of two of the axioms that David Hilbert had in his Foundations for Geometry, which was what Queneau was kind of parodying in his Foundations for Literature. So these two axioms then are, and there are lots of axioms, but these ones are that given two distinct points, there is always a line containing those points. And given any line, any 2 points on that line uniquely determine that line. So 2 points lie on one and only one line. Now, this is certainly true in Euclidean geometry. If you have 2 points, you just can join them with a line, and that defines a line, and those 2 points only lie on that one straight line. It's also true on the non-Euclidean geometry of a sphere, but we have to slightly change what we mean by the words point and line. So a point on a sphere, we have to actually consider it as two antipodal points, north and south pole, for example. And then if you take any other pair of antipodal points on your sphere, then those 2 points, so-called, will define one particular line. And of course, the lines on a sphere are not straight lines, they are great circles, equators. So in that non-Euclidean geometry, as long as we adopt this slightly different definition of point and line, we can still have these axioms holding true. There are even more esoteric, weird and wonderful geometries that we can define, including things like projective geometries and so on. I've got a picture on the slide of a very famous example called the Fano plane. Now, in this geometry, there are points and there are lines, but the points, there are exactly 7 points. And those are shown as little circles. And then there are 7 lines as well. But these lines, they're not all straight lines. So you've got, if you can see the colours on the slide, there's an orange line, there's a yellow line. There's a green line actually looks like a circle to us, but it's still we count it as a line. There are 7 lines, there are 7 points. And the brilliant thing about this is so symmetrical, is that any pair of points lie on exactly one line, following that axiom. Every line contains exactly 3 points, and you can see in the diagram here, there's a lot of symmetry going on. If you have any line, any 2 points on that line will precisely determine that line. So any pair of points lie on exactly one line, and any line contains exactly 3 points, and so this has a lot of symmetry. So this is one example of another kind of geometry, but of course we have to understand what we are saying are points and what we are saying are lines. And the idea is that if you have a collection of axioms, you can say a geometry of a particular kind, like Euclidean geometry, is a collection of points, lines, planes, and so on, that satisfy those axioms. So what Queneau was suggesting in a kind of humorous way is that you could do a similar thing for literature. So instead of points, we now can say words. Instead of lines, you can have sentences. And then those two axioms that I had before, given any 2 points, define a line. Well, you could say a particular literary structure would be a text satisfying a given set of axioms. And so you might, for example, say potential axioms could be, given any 2 distinct words in that text, there is always a sentence containing those words. So points become words, lines become sentences. Given a sentence, any 2 words, I said on that line, but in that sentence, uniquely determine that sentence. So those could be potential axioms. And then you could, for example, you could have a text which is obeying the same kinds of rules as the Fano plane. So I have come up with, for this lecture, an amazing new kind of fiction, an amazing new kind of literary form called Fano fiction, which is based on the Fano plane. So any piece, any text of Fano fiction will have 7 words, and there will be 7 sentences. Okay. Moreover, any pair of words must lie in one and only one sentence. Each sentence must consist precisely of 3 words. So that's quite an ask, because you'll see that I've put some words in a diagram on the slide. The words have to do, a lot of them do double duty, because, I have respected the rule that every sentence has to have a verb in it. But of course, you can't just have verbs in your sentence. So lots of words that I've picked out here, I've got 7 words that are going to make 7 sentences. Lots of these words can be verbs or nouns. For example, best. Something can be the best of something, so it can be an adjective, but you can also best something. So best can be a verb as well. Similarly with top and with book, and fast as well, although I don't think I use it as a verb in my particular example. So let me describe this piece of fiction, this story for you, and you can see that it does obey the rules of the Fano plane. So we begin with a literary agency or a talent agency, and you are employed there and you're being exhorted to get the top act, book the top act, so we can make lots of money. So you do that, and then of course you want this person, you found this amazing reality TV star or something, and you need to make some money off them, so maybe they're going to start producing merchandise or something. You've got to get in there first and fast. So best book fast, you better get that act signed up. So you do that, and then you get them a tie-in with a clothing company, and they sell a line of T-shirts. The top sold fast, so they should definitely write their autobiography now. So next, book sold. Well, what a great success. You've got to act quickly and bring out the next volume of your autobiography. So do that. And then you've got to beat whatever you've done before already. You've got to top your best work and produce something even more amazing. And when your star does this, of course, you can then sell your share of the proceeds and become a millionaire. Best act sold. Okay, I didn't say it was going to be a great piece of literature, but anyway, that's my little tribute to the Oulipo. I've come up with a new form. Of course, if it isn't new, then someone will definitely write in and tell me, is there other Fano fiction out there? I'd be very pleased to see any attempts at it that anyone feels like sending me. Okay, so that's just one example. Obviously, this is an extremely constraining set of rules, and we're probably not going to get great literature out of this, but it's just a fun thing to do. Another place where we see constraints, perhaps less mathematical, but we couldn't talk about the Oulipo without talking about lipograms. So lipograms are texts where one or more of the letters that you normally use, one or more of those is forbidden. So the most famous of these is Georges Perec's book La Disparition, which does not have any E's in it, except on the front cover, I guess. Now this is probably most famous because it abides by one of the precepts given by Jacques Roubaud, who was another Oulipian, who said that actually if you are going to use a constraint, a mathematical constraint of some kind, then firstly, that constraint should be made use of, you should be aware of it in the text somehow. And his other precept, which we'll come up to later, is that you should also try, if you've used some bit of mathematics, which isn't really happening in lipograms so much, but if you use a bit of mathematics, then you should try and use some consequence of that mathematics as part of the construction of your work. We'll see that happening in a moment. But first up, lipograms. Now, This book, La Disparition, satisfies the first of Roubaud's precepts because it is about the disappearance of the letter E, as well as not having any letter E's in it. So that's very nice, and I think that sort of puts it above some of the other attempts to write fiction without particular letters, which in fact had been done earlier in 1927. There was a book called Gadsby, which does not have any E's, but it doesn't quite reach these heights. Now, how hard is it to do this? There are lots of books which miss out particular letters or various other constraints. So there was a sequel to La Disparition a few years later called Les Revenantes, which does not involve, so it uses all the E's that were missed out of the first book, but in exchange, it misses out, it does not have any of the other vowels at all. So it's only got E's. So you could ask yourself, which one is harder to do? No E's or E's but nothing else? And Queneau had suggested this measure of difficulty, the lipogrammatic difficulty of a text. And what it does is to say, okay, we can do textual analysis of, the whole English language or the whole French language, whatever language you're writing in, and we can see what the frequency on average of that letter or those collection of letters is. So the letter E, for example, in English language, about 12.7% of letters in normal English text are E. So it has a frequency of about 0.127, something like that. Whereas W, for example, is much less frequent. It's easier to write text without any W's. You could, just about 2% of the letters are W's. So you have a frequency at which you can measure in your preferred language. And then what Queneau said is that if you multiply this by the number of words in your text, words are easier to count than letters, or I think this is why, then you get the lipogrammatic difficulty of that text, how hard it is to construct. So the text of n words, frequency of letter or letters omitted is F, so n times F would be your lipogrammatic difficulty. So now we can actually determine using this which of these kinds of texts is harder to produce. So La Disparition, no E's. Now in French, E's are more common than they are in English. And the frequency, if you look at all the E's, accents and everything else, it's about 16.7% frequency of E's. The length of La Disparition has been estimated about 80,000 words. So if you multiply those together, you get the difficulty level of 13,373. Pretty difficult. Let's see about Les Revenantes. So this one's got all the E's and no A's, I's, O's or U's, no other vowels. Now, obviously, there are more of the other vowels put together, and the frequency of all of those non-E's put together is about 28%. But, and you'll see there's a good reason, from this lipogrammatic difficulty, the text is a lot shorter, about 36,000 words. I don't have an exact word count, but I estimated based on the page count. This gives a lipogrammatic difficulty of 10,086. So obviously approximation. So because it's a lot shorter, it has a slightly lower difficulty level. This is just an estimate, of course. Now, you could ask about translations. These books have been translated, and I absolutely, it's astounding skill to be able to translate one of these lipograms, because not only do you have to meet the lipogrammatic constraint, but you don't even get to choose what you're writing about. So you have to add on to this the difficulty of translation. And that makes it really, really hard. So you can work out the difficulty levels, just the lipogrammatic difficulty, but I don't think that expresses how hard it is for, George Adair to translate La Disparition and get a Void, or Ian Monk to translate Les Revenantes and get the Exeter texts. There are some other versions, so I've written the names of the translations there. Avoid has no E's, the Exeter text has no anything else's. Eunoia as well is worth checking out by Christian Bock. That's got a chapter for each of the vowels where that vowel and only that vowel is used. So you might like to explore what the lipogrammatic difficulty level of the various chapters are. Well, what next? This is really about fiction, this talk, but I did want to mention poetry because it does have, of course, even kind of standard poetry tends to have constraints, like a sonnet, 14 lines in iambic pentameter, 10 syllables, and there's a rhyme scheme as well. You get more complicated things like sestinas and so on. So just wanted to mention a little bit about poetry here. In particular, there's a collection of poems by Paul Brafort from 1979 that obeys the precepts of Roubaud that you should, if you're using some maths, you should use some consequence of the mathematics. So I just wanted to talk to you about that for a minute or two. So these poems, the English translation of the title is My Hypertropes 21 minus 1 Programmed Poems. And I've just shown the very first of these on the slide. So don't worry if the writing's a bit small, but you may notice that there are some little arrows off with numbers on them, pointing to various numbers. This is sort of directing you to or alerting you to something about the other poems in the cycle. There are 20 poems, but instead of saying 20, he said 21 minus 1. And this is a clue that actually 21 is a Fibonacci number, and so is 1. These poems somehow involve or use the Fibonacci sequence in the structure. And we'll see that they obey this second precept of Roubaud, that because some consequence, some mathematics about the Fibonacci numbers is also involved. So there are these 20 poems. So let me tell you about what the mathematics is. So we know the Fibonacci sequence. Now, you can begin it with 2 1s, but I've chosen to start with 1. So 1, 2, 3, 5, 8, 13. Each number is the sum of the previous 2 terms. So to get from, you get up to 21, the next number is 13 plus 21, that's 34. So that's what we do with the Fibonacci numbers. Now, the bit of mathematics is in tune with some other mathematical things that number theorists like to do. And that is expressing particularly positive integers, positive whole numbers, in terms of your favourite kind of number. So, for example, Lagrange proved in 1770 that every positive integer is the sum of at most 4 perfect squares. So the perfect squares, 1, 4, 9, 16, 25, and so on. So you can write 23 as 9 plus 4 plus 1. Okay, so that's 23, the sum of 4 perfect squares. You can also write 23 as we do in every single day life, and as I have written it there, 23 is 2 tens plus 3 units. You can write it in decimal, in other words, as a sum of powers of 10. You can also write numbers in binary, which is as a sum of powers of 2. The number 1, by the way, is 2 to the power 0, and it's also 10 to the power 0, so that's why I read aloud. So 1, 2, 4, 8, 16 powers of 2. The good thing about the binary expression for a number is that it uses each power of 2 either 0 times or 1 time. So it's a sum of, any number is the sum of distinct powers of 2. So 23, 16 plus 4 plus 2 plus 1. So we've got that distinct way, and there's exactly one way of doing it. So for the binary expansion, any positive integer is the sum of distinct powers of 2 in exactly one way. So Fibonacci. Zeckendorf's theorem, 1972. So just a few years before Braffaut's sequence of poems, Zeckendorf's theorem says that every positive integer can be expressed in exactly one way, there's only one way of doing it, as a sum of distinct non-consecutive Fibonacci numbers. Now that non-consecutive is very important because, of course, you could always replace a Fibonacci number if you could do this by the previous 2 terms in the Fibonacci sequence, because, of course, any term in the Fibonacci sequence is the sum of the previous terms. So we have to say we're not allowed consecutive ones, otherwise we lose the uniqueness, the exactly one wayness. So 23, for example, is 21 plus 2, but we do not allow 13 plus 8 plus 2, because 13 and 8 are consecutive Fibonacci numbers. So Zeckendorf's theorem gives you a way to write everything in exactly one way in terms of Fibonacci numbers. And what Braffaut does in his poems is that, for example, poem 7, you have this breakdown, this construction as a sum of Fibonacci numbers. 7 is 2 plus 5. So poem number 7 has references, allusions to poem 2 and poem 5, and themes recur and come back throughout the sequence of poems. Poem 8 is a Fibonacci number. So for those ones, just to make it a bit more interesting, otherwise 8, it would just be itself, when they're Fibonacci numbers, then he would reference the previous 2 Fibonacci numbers. So poem 8 references poems 3 and 5. So that is just one way in which you can use mathematics, and you can use actually a theorem of mathematics. Now, what I wanted to do in this final bit of this section about using structural constraints is to talk about a book of, popular best-selling book of literature. Steer away a bit from the Oulipo, wonderful as they are, but, I wanted to show that you can use these kinds of constraints in a best-selling book. Okay, so the book I'm going to talk about is The Luminaries, and this won the Booker Prize in 2013. Eleanor Catton's wonderful book. It's about a gold mining town in New Zealand in the second half of the 19th century. The action takes place over the course of a year. There are 12 chapters. Each one takes place over the course of a single day. The constraint I want to mention is that each chapter is half the length of the previous one. And we can discuss, how this affects what the possible length of the book can be. There's a lot going on in the book. There are 12 main characters and 7 other characters. The 12 characters have associations with the 12 signs of the zodiac, and what they're doing in each chapter is affected by what the position of the stars are out on that exact day in time when the chapter is set. There's all sorts going on. There are other characters associated to the sun and the moon. Those are the luminaries, and it all ties together beautifully. So, first question for us as mathematicians, how long is this book going to be? So let's say you start with a chapter of length L, whether that's words or pages or something, just say it has length L. Then the total length of the whole book with 12 chapters, the first chapter is L, then you've got half L, quarter L, eighth L, and so on and so on and so on, until you get to 1/2048 of L for the final 12th chapter. So, okay, that's fine, you could work that out. But this is an example of a slightly more general thing called a geometric progression. So in a geometric progression, we had 1, a half, a quarter. You're multiplying by a half each time. In general, you would have 1, r squared, r cubed, and so on, where r is any old number, and those are the terms. I've taken off the factor of L for the moment. We can add that in later. So the nth term of this thing, so the third term, for example, is r squared. The fourth term is r cubed. The fifth term is r to the 4. The nth term will be r to the n minus 1. If we want to add up all of these and find the sum, there's a really, really brilliant trick to do this. So what we do, for no apparent reason, is we multiply by 1 minus r. So in that equation, you can see I've got 1 minus r times the thing I'm interested in, the sum 1 plus r squared, and so on. And when you do that, you get 1 times this whole sum, and then you're taking away r times the sum. So you sort of shift everything one place to the right. And when you do that, you can see that you can actually cancel almost everything. And the only thing you get left with is a 1 and the minus r to the n. So we can just divide through by 1 minus r at this point and get that the sum is this very simple expression, 1 minus r to the n divided by 1 minus r. Now, in our case, r was a half. So 1 minus a half is a half. So if we're dividing by half, it's the same as multiplying by 2. So with n chapters and r equals a half, so this is our book, the length of the whole book is going to be, if you just work this out, twice L, 1 minus r to the n, so 1 minus 1 over 2 to the n. In particular, it's less than 2L. The whole book in total is less than twice the length of the first chapter, however many chapters you have. So that's a huge constraint. If you read the first chapter, you're more than halfway through the book. Another way of looking at this is if you think, how many chapters can there be then? If we take S to be the length of the last chapter, then there's a simple relationship that our initial L first chapter is 2 to the n minus 1 times S. So the whole length of the book, if we just substitute that into what I've just written, is going to be 2 to the n minus 1 times S. Now, there's a nice little coincidence here in this book, or a deliberate inclusion, that there's a lot going on in this book. It involves this character, Walter Moody, who turns up in this gold mining town, and it uncovers a whole plot involving opium and love and theft and murder and the discovery of 4,096 pounds worth of gold sewn into the hems of some dresses. That 4,096 is involved, as you may already can see. We're trying to work out how many chapters there can be in this book. We know that the length is 2 to the n minus 1 times the length of the last chapter, n being the number of chapters. If there are 12 chapters, which there are in this book, that is 4,096. That's 2 to the power 12 minus 1. So there's that 4,096, a little hint in the text for us. So 4,095 times the length of the last chapter. So that last chapter cannot be very long. Can't be measured in pages, because the whole book is like 830 pages long. if you look at how long a novel can be before, the spine falls apart, it's about 400,000 words as an upper limit. So if S, the last chapter, is just one word, you can solve this equation. You work out 2 to the n minus 1 has got to be less than or equal to 400,000. And if you do that, you get a value of 18 for the upper bound for the number of chapters. But actually, if it was 18 chapters, the whole last 6 chapters would just be 63 words in total. So I can see why she picked 12. Because then, the last chapter then it's actually 95 words, and that is not ridiculous. It's one paragraph. And the reason I think this works so well, this book, it's not a constraint just for no reason at all. The continuous halving of the chapters mirrors the moon as it goes from full down to crescent moon. So it's got this sort of echoes of a lot of the other themes of the novel. It also ratchets up the tension a bit because you get this very big, long first chapter of, 400 or so pages. And then each next chapter is getting shorter and shorter and shorter, and it gives you the sort of impetus through the story. There's a reason for the halving, as we say, for the decreasing length of chapters ties in with what the moon is doing. But also, gradually, as you get to this final chapter, you get to the real kernel of the story. And what it's really about is this love between the luminaries, the characters represented by the moon and the sun. And that final chapter, it's just one paragraph, and it's just those two people talking. And that is really at the heart of the story. So I think this is what makes it works really, really well. It's not just an arbitrary constraint for no reason. It ties in perfectly with the theme of the story and with the narrative arc. That then is a few examples of how we can use mathematical constraints to structure the story and give some formal restrictions on it. What I want to talk about next is how we can use mathematics to actually talk about the plot and the narrative. Let's look at some of the ways mathematics can contribute to the plot and narrative of a story. There's a fun little example that was given by Kurt Vonnegut in a public lecture about how we can actually graph the plot of a story. This isn't really very mathematical, but it's fun to see. So, example, here is a story. It's called Man in a Hole. And so we can see this story on the axis, the x-axis is time. So we're moving along through the narrative. And then on the y-axis, going up is good things happening, and going down is bad things happening. So this story begins with a man who's kind of happy, and then something bad happens, and he gets into a scrape of some sort, and then he gets out of it, and that's the story. The next one, this one's called Boy Meets Girl. So someone's happy, and then they meet someone, and they fall in love, but then they lose them, but then they get them back again, and they're happier than they ever were. See if you can guess the next one. So here's this poor girl. She's very unhappy. Her mother died. The stepmother's really awful, makes her do all the work around the house. Then suddenly there's going to be a ball at the palace, and she really wants to go. She's not allowed to go, but then fairy godmother turns up. Yes, it's Cinderella. She goes to the palace. She's very happy. Then midnight strikes. Oh no, she has to run away. Suddenly the sharp descent of the graph into unhappiness. She's a bit happier than before because she's got her memories, but, never going to be as good. And then, of course, the prince comes and her happiness zooms off to infinity and everything ends marvellously. By contrast, here's the story. Someone's very unhappy, and then one day they wake up and they've turned into a cockroach. So that's, of course, the plot of Franz Kafka's Metamorphosis. Happiness level declines to minus infinity. Another example of a graph of a plot is, of course, in Tristram Shandy, where Lawrence Stern is describing how he has meandered from just telling the story so far. This is in about chapter 40. He might have been born by this point, Tristram Shandy. I can't quite remember, but we can draw these little plot lines. However, this isn't really very mathematical. Let's do some mathematics. Plot trees. So this is used when you have a story and you want to give the reader some choice. So classic example of this is maybe when you were a kid, you had one of those choose your own adventure stories where, get to something would happen and then you say, okay, if you want to talk to the wizard, go to this point. And if you want to instead enter the scary forest, go to that point. And so you're making these choices all along. Now, this tree that I'm showing on the slide is an example of a potential way through a graph through a play where after every scene the audience can decide what they want to happen next. So you do scene one and then you say, okay, do you want the king to issue the decree, or do you want the princess to come running in screaming? And so that the audience choose, and then you do a different scene according to what they say. The problem with that is, now this tree shows working down from the first scene, which everyone sees that. Then there are 2 possible next scenes. Then they make another choice, 4 scenes, 8, 16. The actors are going to complain. They're going to have to learn an awful lot of scenes in order just to have, this is a 5-scene play, and there are 31 scenes to learn. So this isn't very good for the actors. There's a way through this, and this is proposed by 2 Oulipians, Paul Fournel and Jean-Pierre Hénard, called the theatre tree. And this cuts down the choice a lot, but the audience can't tell unless they come and see it lots of times. So in this version, actually, you are given choices, but some of the choices lead back to things that have been arrived at through several parts. So you see with this tree, just like in the previous tree, the audience is seeing 5 scenes and they're making 4 choices. But the full tree had, you still ended up with sort of 16 possible plays, but you needed 31 scenes to do it. This tree, you still get 16 plays, but you only need 15 scenes, not 31. And the way it's done is by having different routes to various scenes. So scene 2, yes, you have your first scene, scene 1, second scene, scene 2, there are 2 possibilities. But then you get a choice at the end of the second scene of either one of 2 possibilities, but they lead you to the same 2 scene 3s that the people who are seeing the other version of scene 2 are going to get. So there's a way through this. It's slightly complicated, but you can see there's a lot fewer scenes for the actors to learn because some of the choices will lead you back to other scenes. And, Fournel says that actually, if you wanted to make 16 5-scene plays, normally that would be 80 scenes that you have to write. But this saves you so much time. Mathematics saves you time because you're only having to learn and write 15 scenes. So these are kind of ways in which the audience has a lot of choice. Another thing that can happen is that you can be given routes through a text. So either determined by the author or with some choice. So an example of this is reverse poems, which are quite popular. So I won't write down a whole poem, but there's one, for example, called Lost Generation by Jonathan Reed. And the idea with these is that you read them through from top to bottom in the normal way. And then when you get to the end, it says, now read it in reverse. And, normally the first read through is very pessimistic and reading backwards is optimistic. So the first 3 lines of this Lost Generation poem begin, I am part of a lost generation and I refuse to believe that I can change the world. And some other stuff. But then when you read it backwards, those become the final 3 lines and they read, I can change the world and I refuse to believe that I am part of a lost generation. So uplifting message. Another potential route through a story is the Mobius strip stories. So I guess the most famous of these is Frame Tale by Barth. And in that one, so you get given this piece of paper and you're instructed to cut it and then twist it and then glue it together to itself. And it reads the whole story. So on one side, it says once upon a time. And then when you make the Mobius strip, it says there was a story that began. So then you then carry on and you get once upon a time and there was a story that began once upon a time. There was a story that began once upon a time. There was a story that began. So it's an infinite regression of nested stories that goes on forever. A frame tale, by the way, is a story within a story. There's a more mathematical variant of a Mobius strip story, which is a story called Mobius the Stripper. And that I've put a reference to it in the transcript. So it's got kind of a top half and a bottom half of each page. And once you read the top half, you can then read the bottom half. So it's sort of making a Mobius strip kind of structure, because the Mobius strip, of course, although it looks like at any one point it has a reverse, but if you follow the whole thing round, you will cover both sides of this thing. It really only has one side. So with this Mobius the Stripper story, you read the top half all the way through, and then you come back and read the bottom half, and then you can read the top half again. And there are sort of links in the text between the halves of the story, mirroring this fact that in a real Mobius strip, you do at any point have kind of a reverse and underside of that point. But perhaps more mathematically, even than that, how about 100 trillion poems? Now you can see on the slide the way this has been done, and this is Raymond Queneau's little booklet, 100 000 milliards de poèmes. So what he has done, and you can, the picture tells 1,000 words. There are 10 sonnets in this little booklet, printed on consecutive pages, and you can move all of the lines around individually. So you've got these 10, 14-line sonnets, and what you do is you can make your own poem, many possibilities, by choosing which of the 10 possibilities for line 1, which of the 10 possibilities for line 2, and so on. And so at each point of each of the 14 lines, you have 10 choices. So how many poems are there with these 10, 14-line sonnets over 10 pages? There are 10 to the power 14 potential poems, because it's 10 for the first line times 10 times 10 times 10, 14 times. That is a big number. Queneau did a calculation about how long it would take to actually read all of these potential poems. And we have to ask ourselves, did he write all these poems? Can he be said to have written all of these poems, or did he somehow write the potential for the poems? What counts as writing a poem? The calculation is that you could read a different sonnet every minute for 190 or so million years. So that is a long time. But that's nothing. That's nothing, Raymond Queneau, compared to B.S. Johnson's book, The Unfortunates, because this was a book in a box. There are 27 chapters. There is a first chapter and there is a last chapter, but the middle 25 chapters you can read in any order. So that means there's 25 choices for chapter 2, 24 for the next one, times 23, times 22, and so on. Mathematically, we'd call that 25 factorial choices of ways you can read that book. So how many potential books are there? Well, it's a lot. It's 1.55 times 10 to the power 25. So 25 zeros after that one. That is vastly more than anything that could be contained in our universe, really. And it will take you a very long time to read. You have to read sort of 70 trillion books every second until the Earth is engulfed by the sun. So, we haven't got much time. So the huge numbers of things can be produced by randomness and by allowing any combinations. Another bit of mathematical structure that can be used to kind of create the structure of a book and of a narrative are things called orthogonal Latin squares. So the aim with these things, I'll explain what they are in a second, is that you have lots of different narrative elements. So you might have characters, or you might have particular characteristics of people, someone being angry, or events, or anything like that. And you want to combine them in all possible ways so that different things sort of intersect in all possible different ways. And the mathematical bit of kit that we need to do that is called an orthogonal Latin square. And there's an example of this on the slide where you've got 4 by 4 square, and in each row and in each column you have 1 ace, 1 king, 1 jack, 1 queen. These are cards. And you also have one of each suit represented. There's 4 suits, spades, hearts, clubs, and diamonds. So you've got 2 collections of 4 objects, and you have exactly 1 of each pair represented in the square. But you also have this Latin square thing going on. It's like a Sudoku grid where each thing appears once in each row and in each column. So once in each row and each column, you've got an ace. Once in each row in each column, you've got a king. Once you've got a queen. Once you've got a jack. But you also have this other collection of things, the suits of these cards, that also have that property, and each pair occurs exactly once. Now, it can be shown, Catherine, Oller and Shaw, British mathematicians, show that there are 144 different 4x4 orthogonal Latin squares. And this example is just one of them. Now, Euler, the mathematician, was investigating Latin squares, these orthogonal Latin squares, sometimes they're called Greco-Latin squares or bi-Latin squares, a long time ago, and he knew about the 4x4 ones. He was trying to work out what other sizes there could be. Is there always one of these of order n? So, is there a 5x5 one? Is there a 6x6 one? Euler showed that actually when n is 2 and when n is 6, there are no orthogonal Latin squares. You cannot do this thing. And he conjectured, 2 and 6, they are both 2 more than a multiple of 4. I conjecture, he said, that there are always going to be solutions to this, except when n is 2, 6, 10, 14, and so on. So this is his conjecture. There's definitely aren't any when n is 2 and when n is 6. Now, fast forward a couple of hundred years, and a 10 by 10 orthogonal Latin square was found in 1959, to everyone's surprise, perhaps. They do exist, and actually 14 and 18 do exist as well. So Euler, for once, was wrong. He wasn't often wrong. He was wrong in this one. There do exist 10 by 10 Latin squares. And this was found in 1959. published in Scientific America. The front cover of Scientific American in, I think, November 1959 had a 10 by 10 orthogonal Latin square. Georges Perec used such an object in his book Life, a User's Manual in 1978. And it's got a lovely, lovely structure. The action takes place in this building, which has 10 stories, and each one has 10 rooms or apartments on each level. So you've got these 10 by 10 building. And the chapters each have unique combinations from lists of 10 things. So there's lots of lists. It could be different types of fabric or all sorts of things, but there are lists of 10 things, and chapters will have unique combinations based on orthogonal Latin squares. Another cool thing about this is that actually the stories follow a knight's tour of a 10 by 10 chessboard. I will just mention, there are, in fact, you might expect 100 chapters, right? There are 99. And Perec says, for this, the little girl on pages 295 and 394 is solely responsible. So to know more, read the book. All right, I want to mention 3 more little places where mathematics has appeared and has sort of influenced the plot of novels, or been part of the structure of the novel. The first one, so we're going to go from most popular to more perhaps esoteric. And the most commonly occurring of these, or most popular one of these, is Jurassic Park by Michael Crichton, which of course several films and things since it was written. And it incorporates into its structure the idea of a fractal, because a lot of the theme of the story is about, if you think you've got a system that you understand and can control, actually within it are the seeds for chaos and losing control and not knowing what's going on. I do have to say, unfortunately in this book, people do get eaten by velociraptors. So, be aware. It can be dangerous to ignore the warnings of mathematics. There is a fractal in the book, and it appears, gradual iterations of it appear at the starts of various sections of the book as the initial perception of having control over the system that you're working in at a theme park full of dinosaurs gradually starts to go awry. And the curve that was used, the fractal that was used by Crichton in this, is called the dragon curve, which of course is appropriate. And it's an amazing thing. So you start off to make this several ways, but one way is you start off with just a flat piece of paper and you keep folding it over in and itself as shown. And then once you do, sort of crease all the folds, and then you unfold it and see what the paper looks like. And it gradually takes on this rather complicated form. And you can actually write down an iterative algorithm for constructing this thing without actually folding pieces of paper. And this is shown on the slide. So you start off with just one fold, and then for each straight line, you replace a straight line by kind of half a square. And you alternate whether that half a square appears on the right or on the left of your original line. And you just keep doing this. And this is what fractals do. They iterate, they have recursive processes. And if you keep going, you can see that pretty soon you get something that looks extraordinarily complicated and has this strange kind of structure, and it has this self-similarity as well. It's a fascinating example in this so-called dragon curve. Starting from a simple idea like folding a piece of paper, you get to this uncontrollable situation. You don't really understand what's going on. So that is also the theme in Jurassic Park. And these pictures of dragon curves iterations appear in the book at each subsequent section. Okay, the next one is, I've called it Death by Non-Transitivity. So I don't actually want to tell you what book this is in, because it's a murder mystery and I don't want to spoil the surprise for you. But I will give you the clue that it is in one of the books by Catherine Shaw, that's a pseudonym of the mathematician Leila Sheps, who has written several murder mystery stories featuring a young woman called Vanessa who kind of fights crime and solves mysteries. And in one of these books, and I won't tell you which, there is something called non-transitivity. So in normal life, if we've got, say, we're comparing numbers, if A is bigger than B and B is bigger than C, then that means that A must be bigger than C. And if I'm taller than you, not very likely, and you're taller than Bob, then I must be taller than Bob. This is transitivity. That's the idea of transitivity. Now, we can try and understand this in lots of other contexts, things being bigger than and comparing in size. Have a look at these 3 dice here. So we could play a game of dice and we could each pick one die. So maybe I pick A and you pick B, and then we throw them and whoever gets the highest score wins. We can keep doing this several times. And of course, either of us could win because there's different numbers on the dice. We can keep doing this a few times and we can work out which of these dice is better in terms of which one will win more often. Okay, so let's try this out. If we're going A versus B. So A has, now I can't obviously show you all the sides, but I can show you on die A, there's a 2, but opposite there's also a 2. So it's got 2 2s and 2 4s and 2 9s, okay? And the same with B. They've all got the same thing on opposite faces. So B has 1 on the top and the bottom, 6 on either side, and 8 front and back. So that means there are 9 possible outcomes for this game of dice. So in this table, in the column, the rows are labelled by what A could throw, 2, 4, and 9, and then the columns are labelled by what B could throw. So if A throws a 2, A will beat B if B throws a 1, but otherwise B will win. If A throws a 4, 4 beats 1, but otherwise B wins. If A throws a 9, though, 9 beats everything on B, so 9 will win. So if you look, actually 5 of the 9 possible outcomes are good for A. So A wins 5/9 of the time. That's more than half the time. So we can say that A beats B. Okay, we can do this again. What about B compared with C? So if I'm going to choose the dice, maybe I choose A. And if you have B, then you're not happy. If I choose B, what should you do? Well, let's see. You don't want to choose A because we know that A beats B. So what about C? Well, you can do this kind of calculation. Actually, B will beat C because if B throws a 1, B will lose. But if B throws a 6, it'll beat C twice. And if B throws 8, it'll beat C always. So again, 5/9 of the time, B will beat C. So A beats B and B beats C. Therefore, A beats C, right? No. Actually, if you calculate it, you find that C will beat A. So this is a non-transitive set of dice. A beats B, B beats C, but C beats A. So all we have to do now is to change the word beats for the word murders, and you get this setup of a murder, a series of murders where somehow A murders B, B murders C, but C, who ought to already to be dead, somehow still manages to murder A. So think about how that might be done, but Catherine Shaw finds a very elegant way in one of her books. Okay, finally, and perhaps most esoteric, let's go back to the Oulipo, or actually the Oulipopo, because the Oulipo actually had several branching off kinds of things, all coming under the umbrella of Ouexpo, the ouvroir de X potentiel, whatever X is. So you can have Oubapo is bande dessinée, cartoons, and Oulipopo is potential police or detective fiction. And one example of this is the story by Claude Borges, Who Killed the Duke of Densmore. So Oulipopo is littérature policier potentiel. So this is a story that uses graph theory. So in this story, the Duke of Densmore has been killed and he's been dead for like a decade, but it's still unsolved. The great detective is trying to solve this once and for all. So what we know is that each suspect of the murder, which are all kind of the girlfriends of the Duke, stayed once at the Duke's house during the time leading up to the murder. And everyone remembers, it's a long time ago, so they don't remember exact dates or times that they were there, but they do remember who they saw when they were there. This results in what we call an interval graph. So an interval graph is where you have a collection of intervals, maybe on the real line, or intervals of time. And what you do is you see if any of them overlap. And if they do overlap, then they're linked. And so you can turn this into a graph where the vertices are the intervals of time, and then you join any pair of vertices with an edge if those intervals overlap. So if you had the interval, say, 12 o'clock till 2 o'clock, and then 1 o'clock till 3 o'clock, they would overlap with each other, so they would be joined by an edge in the graph. So I've got here just a toy example of 4 people. It's suspects, A, B, C, and D, or Anne, Beth, Claire, and Daisy, let's say. And what this graph is telling us is the information that Anne claims that while she was there, she also saw Beth and Daisy. Beth is claiming that while she was there, she saw Anne and Claire. And Claire says that while she was there, she saw Daisy and Beth, and so on. So we can draw the relative lines and so on, and we can get this graph. It's called an interval graph. Now, graph theorists have studied interval graphs, and there is a theorem which was known to the author of this story, Borges, that says we actually can eliminate some graphs that cannot be interval graphs. For example, there are some properties. Graph theory is cracking the case for us here because there is a theorem from graph theory that says interval graphs have to be chordal. It means that every circuit, like we've got in that sort of square graph in the picture, that can't be an interval graph, because every circuit like that must have a chord in it. You ought to be able to break it up into triangles, basically. And this is not the case for the graph I've shown there. What that tells us is that at least one of these suspects is lying, because that is not a valid interval graph. But in the actual story, it's a much more complicated graph with more suspects and so on, and a stronger result in graph theory is used to actually say not only someone is lying, but you can pinpoint who is lying, and then, of course, they're the murderer. So this is using a theorem of graph theory. It's one of Roubaud's precepts. We're using some of the maths in the story. Well, that's another context then in which mathematics can help us to give structure to a story. So we've seen the structure of a story can involve constraints. Another concept of the structure of a story is the way in which we put the story together and make the narrative. The final variant or understanding of this phrase, the structure of a story, is the structure of a story. And for that, we're going to talk about the Library of Babel. The Library of Babel is a short story by the Argentinian author Jorge Luis Borges. And it's about a world in which the whole universe is a library. How wonderful is that? The first sentence says, the universe, which others call the library, is composed of an indefinite and perhaps infinite number of hexagonal galleries. And it's told from the point of view of one of the wanderers in this universe, a librarian, who spends his life traveling from room to room, looking at the books, studying them, trying to understand the structure of the universe based on that. He bumps into other librarians from time to time. There are some textual hints as to what the library is like, and it gives us enough information to deduce something about the size of this library. We have some questions. How many books are there in this library? How many hexagons are there, these hexagonal galleries? And then what shape geometrically is the library, given the various other constraints that we're given? So how many books? I mean, you could say, well, who knows? But actually, we have some very detailed information from the story. And here it is. So each book, we are told in the story, all the books are the same size and shape. All of them have 410 pages. All of them have 40 lines per page. And all of these lines have 80 characters. We're also told that there are some characters on the spine. It's not specified exactly how many, but I kind of thought that because there are 40 lines on each page, perhaps there are 40 characters down the spine. And we are told that there are 25 possible characters. So 22 letters and then space, comma, and full stop. And that's it. So every one of these characters, there are 25 choices for. And we are then crucially told the library has exactly one copy of every possible book. Okay, so that enables us then to count how many books there are in this library that is of indefinite size and possibly infinite. Well, is it? Let's see how many books there are. So in a book, we need to know how many characters there are. So on each of the 410 pages, there are 40 lines with 80 characters. So you multiply those together, then you add the 40 for the spine, and the total is 1,312,040. So how many books does that mean there are? Well, it's a bit like with our sonnets. We do this multiplication. Each of these 1 million characters, there are 25 choices for. So it's 25 choices for the first character times 25 for the next times 25 times 25. It's this huge power of 25. 25 raised to the power 1,300,000 and so on. Approximately that's 10 to another vast number, 1.8 million. The reason I converted it to a power of 10 is just to remark that there are 10 to the power 80 atoms in the universe, roughly. So this library cannot exist in our universe. It's in a separate universe, which, is said in the book, this is the universe, which we call the library. So that's a vast number of books, but it is finite. There is a finite number of books, and therefore the library must be finite. Now, question immediately, we are told as well how many books there are in each hexagonal gallery. Does this number 25 to some huge power correspond to a whole number of hexagons? Slightly problematically, not unless we tweak things a bit. So we are told each hexagon is identical, and that on 4 walls of the hexagon, of any hexagon, there are bookshelves, and then the other 2 walls have no bookshelves. The total is given as 160 books per wall of the 4 walls, so that gives you 640 books on each or in each hexagonal gallery. Now, 640 is even, but 25 to any power is an odd number. It's just a load of 5s multiplied together. So this does not compute. There can't be a whole number of hexagons, which does not make sense when you have in the story told that the library looks exactly the same in all directions. Everything is identical. All hexagons are identical. It continues infinitely far up and infinitely far down in all the directions. How can this work? So I have a suggestion for this. My suggestion is that titles of books don't usually have full stops. So perhaps if we say that the characters on the spine can only be one of 24 possibilities, that gets us out of the trouble. I don't know what the right answer is, but this is my suggestion. In that case, for those 40 spine characters, we have 24 choices each. So that's 24 to the power 40. And then the remaining one, some huge power of 25. That allows you to then have a multiple of 640 because you can get all those 2s that you need to make 640 from the 24s. So with that little tweak, which I hope will be allowed, we can get a whole number of hexagons. But then how are they configured? Well, we're told something more about the hexagons as well. What are we told? From the text, hexagonal galleries have vast air shafts between them. So let me show you a little picture. So the air shaft between them, which are surrounded by a low rail, go up and down as far as the eye can see. So that means that sort of any hexagon has above and below it going on forever, hexagons positioned in the same way. The 4 walls that have bookshelves on, we know about. On the other 2 walls, these 2 free walls, you've got doorways leading to other hexagons via a hallway which also contains a spiral staircase that takes you up and down, so you can move up and down. So the fact that these staircases are positioned in all the hallways and you've got these air vents means that actually the design of any floor of this library must be the same. All the floors look the same. Now we can then think about what do the floors look like, and there is some, again, it's not quite clear. What I've chosen to think is that these 2 doorways coming off each hexagon are just on opposite sides. This gives you a kind of a long strip of hexagons. There are other configurations. If, for example, the doors were on adjacent sides, you could get different things happening on the floors, and those are things to explore. I recommend the book by William Block for this, who goes into a lot of detail. So that's one possibility. You get sort of chains of hexagons on each floor, and then that's replicated. So if you can imagine what we're going to have in the library, and I will show you how I think one way that the structure could work is this. Initially, imagine just a rectangle with rows of hexagons, and then you go up, and there's another one, and another one, another one, going up and up and up and up, and the rows are going to the left and right forever. Now that's the problem. I've gone on the left there a rectangle that seems to show forever, but of course that rectangle is finite and it stops. So we know the library is finite. You're going to hit the top row, the top level, and then there's the ceiling, right? But that is not what happens in the story. The story says it goes on forever in all directions. So what can we do about this? So one possible solution that you can have to this is to kind of topologically speaking, what we're going to do is to just say that the top and the bottom of this rectangle are just the same as each other. We're going to identify them in space. So topologists have no problem with doing this, but conceptually we can think of this as kind of wrapping it round to make a cylinder. So that you can imagine just keeping on going, and you can keep on going round and round and round and round, round and round this circle forever, and you never get to the end of it. Kind of like we do on the planet Earth. You're never going to get to the end of planet Earth, even though the surface of the Earth is finite. So that's the first step. And that gives us, we can keep going up and up and up and up forever and ever and ever, and we'll just loop round. This won't be absolutely identical on all levels if we do it kind of in our 3-dimensional universe, but there are ways around that if we're allowed to move into higher dimensions. But then that still means you could run out of space on the left and the right. That's okay too, because then we can do exactly the same thing as I've just said. We can then sort of identify those ends of the cylinder that we now have with each other. So kind of wrap them around, and we get kind of a torus shape. Again, you would get some distortion if you try to do this really in 3-dimensional space, but if you do it in 4 dimensions, there are ways to make it so that you don't get any distortion. So this means that now you can carry on, you have a sort of a horizontal circle and a vertical circle, and the library really can continue forever. Now, there are many other possible solutions to this, and so this is why I think we need an Oulipo, an ouvroir des bibliothèques potentielles, a workshop for potential libraries. But that's just one little lovely short story by Borges that has a lot of mathematical ideas inside of it. That's all I have time really to talk about in terms of mathematical structure. There's lots of references in the transcript that you can look at, and I hope you've enjoyed exploring some of these ideas. Please do send me your Fano fiction if you feel so inclined. So just a heads up for my next lecture, where do mathematical symbols come from? That's on the 27th of April at 1 o'clock. You can sign up at Gresham as usual to watch it live. Also, I'd suggest if you follow Gresham College and or me on Twitter, we can alert you to any other future lectures that might be of interest for you. It's such an interesting topic about mathematical symbols, where we get the equal sign from, who invented it, why do we use pi for the ratio of the circumference to the diameter of a circle, or even if you just want to know what zenzi zenzi zenzica means, do tune in next time to find out.